look at how to sketch a derivative. So what you're going to want to do is you're going to want to either do this in Notability on a separate sheet of paper, and just, I would probably easier to do it maybe in, I guess I really don't care, just call it sketching derivatives. And I've got an applet that I use to demonstrate this, because when I did it when I was in high school, they were trying to explain it all verbally, and it was really confusing. Okay? So what I want you to think about is, let's go back to just derivatives. We're not doing related rates. We're not doing implicit differentiation. Just think back to derivatives for a moment and think about what a derivative is. The derivative represents the what? Slope of the tangent line. But what you've got is got a point with an infinite, you've got a graph with an infinite number of points on it. So, if you will, this graph has a point there, this graph has a point there, it has a point there, it has a point everywhere, a point here, a point there, a point everywhere, a point, point. Okay, so it's got all of these points, all right, all over the place, and each point has a slope. And the thing that's interesting about curvy graphs, or graphs that are not straight, see, lines are boring because they're straight, so the slope of the tangent line is just the slope of the line. But when you have graphs that are not straight, when the lines are curved, okay, like in this example here, the slopes are changing at every point. And so what I want to do is I want to take a graph and I actually want to plot out what the derivative would be. And I'm going to do it for a few points just to illustrate what I'm trying to show you. And I'll pick some points here. I'll use blue, okay, just to contrast with the red. So I'm going to pick a few points just randomly, and I kind of know what points I'm choosing on purpose, just so you can get an idea of this. And then I'm going to show you how this applet works, and I do have a link to it. It doesn't work on your iPad because it's flash-based, but if you go to a computer, you can mess around with this applet and kind of see it and go through it. If you have a phone that's non-Apple and it runs Flash, you can do it. But if you think about this point here, what would you guys estimate the slope to be? First of all, what would you say about that slope at that point? It's positive. It's definitely positive. Now, whatever that x value is, I want you to imagine whatever this x value is, I don't care what it is, it's -7, -10, whatever. All right? So whatever that, well, it couldn't be -10, so like -9, okay? So whatever this x value, that x value has a slope at that point. And you guys are saying that slope is approximately what? Positive what? Positive 4. So what you do when you plot a derivative is you actually plot, it forms a point. So when you pick these points, so if I'm picking an x value for the derivative, so at -9, what this y value becomes is it becomes the slope at that point. So this y value takes on the slope at that point. So you guys are saying that's a positive 4. So when you go to plot the derivative, at -9, you're plotting a positive 4, which we'll just say is roughly here. So there's a point on the derivative. Now what I want you to notice is that if you pick any point below, well, let's do another one just to make sure. Let's say this is at -7, okay? Let's say this point is at -7. What would you estimate that slope to be?
3.
It couldn't be as steep as this one. This one's steeper, right? So if we said this one's 4, we have to say this one's less than 4, right? So it could be anything. It could be 3, 2, whatever you want, as long as it's less than 4. So that's a positive 3. So now when we go up here and we plot the derivative, we're going to go down just a little bit. And what's going to happen as we go, these slopes are all positive. What's going to happen is as we go further and further and further and further and further towards the peak, these slopes are going to approach what?
0.
They're going to approach 0. So at this point, let's say this is -5. That slope is what? 0. So when we plot that point, we should cross the x-axis right there. And what happens is as we plot out these slopes are going to start approaching 0. Because you're plotting out points. You're actually plotting out the points for the derivative. And the points for the derivative are formed by taking the x value, figuring out the slope of that x value, and that slope becomes the y value for the derivative at that x value. Okay, let me illustrate a couple more because it doesn't click always right away for a lot of people. So, like for example, this one right here now, if that's, let's say that's -1, I don't know what it is, but what would that slope be? -2-ish maybe? So we're going to say, okay, at -1, then we're going to say, all right, that slope's -2. So we're going to say just this derivative is kind of sneaking towards this value there. And what's going to happen, all these values between here are going to have negative slopes. And what's going to happen, these negative slopes, they go negative, but then they approach what again?
Zero.
Slope of 0. Then at some point it's going to have to sneak back towards what? 0 across the x-axis. Because I know at whatever this x value is, let's say that x value is 1, the slope's 0 again. And then what happens here is now the slopes go what? Up again, positive. And if you like take this point here, the slope is positive 2 maybe. Here the slope positive 5 maybe. And what happens is this graph goes up forever. The slopes are going to start approaching what? Positive infinity, so then the graph's just going to go up. And so that blue thing that you're seeing right there is going to be the graph with the derivative. Hello? Yeah. Sam, go to the office real quick. So what happens is that blue graph is a plot. Listen, the derivative, the graph of the derivative represents a plot of all the slopes from the original function. You're plotting out all the slopes from the original function. So if you go to every x value, you figure out what that slope is, and then you're plotting it as a point. Okay? Now, this applet does a really nice job, and you can see it, and I'll drag it now, and I'll slide it. And there's a bunch of examples that you can go through. So the original function is f, and what I want to do is I want to plot the derivative. The derivative is going to show up in green. All right, you ready? Here we go. I'm going to start dragging it, if I can. Grab it. All right, there we go. So it approximates the slope. So right there it's saying at that point the slope is 5. So then it plots that point at that x value. It plots that slope, so 5. And then it plots slopes, slopes, slopes. Now there's an infinite number of points, which means there's an infinite number of slopes. So your derivative is going to be continuous. It's going to be a continuous graph. And what happens, notice it's getting, and it finally hits a slope of 0. So at that x value, at that particular x value on the red graph, the slope is 0. So at that x value on your derivative, you're going to have to hit a y value of 0 because that y value now represents the slopes from the original graph. So when you're looking at, if you're looking at a table for the green graph, it's not xy, it's xy prime. That's how you're forming your points. Okay? So if I keep sliding, come on, grab it. Grab it. Grab it. You can do it. There we go. I'll eventually get it. I need to just calibrate. I'm too lazy.
You still haven't done it.
Oh, it was.
So I'm going to grab it. Be much easier to do it like this. So as you plot out the slopes, notice as you calculate the slopes, it's plotting those slopes as points at those x values. Then you get to a slope of 0. Now what happens? You get negative slopes. Notice the derivative dips down below the x-axis, reaches its steepest negative slope, and then it starts going back to a slope of 0. And then when it hits a slope of 0, then it's going to hit the x-axis again. And then it goes to positive slopes, which means the derivative is just going to go above. And then it goes off. And that green graph is your derivative. Now, what I want you to notice, a couple things that will help you here, is that when the slopes are positive, notice your derivative is above the x-axis. That's really important. I mean, that's like one of the most important things you got to learn. Okay, because that's going to come in pretty much all next week, the next couple weeks. And pretty much the end of the trimester, everything we're going to do is going to be related to interpreting what the derivative tells you about a function. So when the slopes are positive, the derivative is above the x-axis. When the slopes are negative, the derivative is below the x-axis. And when the slopes go positive again, the derivative is above. Notice the derivative crosses the x-axis when you have slopes of what? 0. So those match up. If you follow the slopes of 0, you're going to cross. If you go straight down from that point, okay, you're going to hit the x-axis. If you go to slope of 0 here, you're going to hit the x-axis. And then everything in between there, you say, okay, the red graph has negative slopes, so the green one should be below the x-axis. The red graph has positive slopes, so the green one should be above the x-axis. The red one has positive slopes again, so the green one should be above the x-axis. And that's the idea here. That's how we're going to sketch a derivative. And we've got tons of practice for you to do. There's not a lot of work to show, it's just sketch the derivative. What are you going to sketch? All right, let's go to the next example. All right, here's one. Now I'm gonna have you start trying to figure out what you think this would look like. So go ahead. This first guess you're gonna make is probably gonna be awful, but at least you take a shot at it.
Go to the bathroom.
Yeah. Oh, did you text me Moser's number? I saw that.
Yeah, we needed to ask him if he could change the test date.
Glad I didn't give it to you.
Did you change it?
I should calibrate my board while I'm waiting.
What was this test?
Let's see here. Okay, give it a whirl and let me calibrate. Hopefully you got something down by now. It's gonna be an awesome video to watch for the wrestlers. You let Patrick and Colin. And is there anybody else I guess I could look to? Managers go managers. Marley. Patrick was really concerned this morning. He was like, "You're gonna videotape, right?" I'm like, "Yeah." All right, here we go. So watch carefully. Now this has what kind? First of all, as you do this, and ask yourself, what kind of slopes does it have? Positive or negative? What kind of slopes are we starting with? So where should your derivative start?
Super negative.
Super negative, and it's below, and it should be not just below, but super below, because this is really steep negative, and we're going to approach zero. Now, I think what helps, I'm going to tell you, I'm going to give you a hint here. What really helps is you'll find all the places where the slope is zero first, and then put where it crosses the x-axis. So it looks like we reach a horizontal tangent here. So right there, we're going to cross, I'm going to use a different color. We're going to cross the x-axis right there. Looks like we're going to have a horizontal tangent there, so we're going to cross the x-axis there. So if I take a shot at this, this is what I think it's going to look like. Are you ready? It's negative, and it starts out super negative, so I'm going to go negative. And then it goes, stays negative slope, so it comes back down. Goes negative, but then it has to approach a slope of zero, so I got to turn, go back to zero, and then it's going to go steep positive. Did anybody get that? Wow, that's pretty good. 3 on the first one.
Oh,
That's a pretty good run. How many of you got that first time? 4. 4 people got it first time. All right, let's see if you were right. Let's see if I was right.
Actually, no, that's 3 because I messed up.
Ready? You watching? Look, steep, really steep negative, super steep negative. So it's got to start way below. Come hit a slope of 0. Bam. Then it goes negative, and it only gets so steep negative, and then it's got to start sloping back towards 0 again. Then it goes steep positive.
wait, why does it turn so early?
Because it only gets so steep negative. Maybe this slope only reaches a slope of -2 or -1. Not very
Oh.
steep negative.
It seems steep.
It seems steeper, but it's not. Okay, all right, here we go. Your eyes playing trick on you. This one's easy. Don't say nothing. Do it. I'll give you all about 15 seconds. This and you'll kick yourself. You ready?
I know what.
All right, what do you think, Max?
It crosses the y at like 2.
Wow, I totally got that
Why is it a horizontal line?
wrong.
Slope
Because
because the slope is the same all
Ah.
the way through the line.
That's always right.
I know some of you drew the line again. Because you're like, well, you told us that the slope of the tangent line is the line itself. Yeah, the slope of the line, not the line. Okay? Think about it. Whatever the slope of this line is going to be, what is the direct? Think about your equations. If this is the equation y equals 2x, what would the derivative of 2x be? 2, a constant. Therefore, your derivative should be constant, which means it should be a horizontal line. When you do the derivative, when you sketch the derivative of any line, it'll always end up being a horizontal line because its derivative will be constant. Okay? So that's that one. And whatever you approximate the slope to be, it looks like they're approximating the slope to be 2. So I'm just going to put my horizontal line at 2. Now there's going to be no wrong answer necessarily. There won't be a perfect answer except for mine, because I'm the one making the problem, because you're going to have to estimate. And if you look at my line and you say, I think it's a slope of 3, but I got it at 2, am I going to count it wrong? No, as long as you have it positive. As long as you know it's going uphill. I know it's a constant somewhere above the x-axis. I'm not going to get too caught up in, did you get 3? Because I'd probably put a slope of 1.3 on you. Or I was thinking a slope of pi. Whatever you're going to be thinking, I'm going to be thinking something else. Okay? Because I'm going to make sure nobody ever gets what I get.
You're gonna have a decimal like up.
Yeah. Even if you do guess the right one, I'm still going to think a different thing.
You're gonna change your mind.
I'm going to change my mind. All right, try this one. This will bring up some interesting conversation.
Are they open?
I'm going to answer that question.
Conversation.
This is going to bring up interesting conversation, which you guys were awesome at on the test. Now, this is a v. I want you to think back to, remember we're taking a derivative. And I want you to think now, you ready? I'm going to say something and it's going to automatically cause everybody to erase probably. Derivatives don't always exist. Especially at certain points. Because there are things called points of non-differentiability. And this particular graph has a point of non-differentiability. Can anybody remind me what the points of non-differentiability are? Corners,
Jump, cusps.
cusps,
Cuspy corners.
vertical tangencies, cuspy corners, and any kind of discontinuity. Now, do we have any discontinuity that you see?
Jump.
I don't see any discontinuity right now in front of me. That red graph, there's no discontinuity. There's no hole, there's no jump, there's no vertical asymptote. Now, it's derivative because if the function is non-differentiable, its derivative is going to be discontinuous. Guys, when you have a point of non-differentiability, a jump, a corner, sorry, say that again. If you have a point of non-differentiability, a corner, a cusp, a vertical tangency, or a discontinuity, the derivative will automatically be undefined at that value. So where is the derivative going to run into a problem? At 0. And what's going to happen is there's going to be a drastic change in slope. What would you approximate this slope to be? -1, so you're going to have a horizontal line at -1. What about this one? 1, so this is what it's going to look like. Boom! And these are not connected. They're not connected, it just, the applet does that because of the programming on it. They're not connected. What it ends up being is it ends up being a jump at 0. And to clarify, not only is it as a jump, is if you remember y equals the absolute value of x, does anybody remember the derivative rule for the absolute value of x? This will be a stretch. Neither do I. Can somebody look it up?
What are we doing? You never actually taught us that one.
Yes, I did.
What are we doing?
I didn't teach it to you.
Oh,
In fact, it's in your notes. It was an example in your notes. We just never did any homework problems with it. You weren't here when you learned it. You were gone.
I have a note card. Wait.
I bet Danny's got it.
Back.
Here.
U
Thank you.
over.
U over the absolute value of U times U prime.
Okay, now if you do the derivative,
Zero.
huh?
It just says you can't.
Yeah, you can't be 0, which is what I want to bring up here. So when you do the derivative of this, it's u, which in this problem is just what? X over the absolute value of x times the derivative of x, which is just what? 1. What ends up happening, because I want to talk about, there is a jump there. It's piecewise, and what you end up getting is your derivative. Your derivative equation is just x over the absolute value of x, which is actually piecewise. And what you end up with is x over positive x if you assume x is greater than 0. And x over positive x is just 1, right? And then if you assume it's negative, x is less than 0, it'll be x over negative x, which is -1. Does anybody know why I do not put an equal to? Because x cannot equal 0, because even though I canceled it, where did x show up in the original problem? In the denominator. Just because I cancel it just means, canceling means there's a what? Hole. When you cancel something, there's a hole. Okay? So that means not only is there a jump here, these points on your paper should be open. Okay? Help me remember that one, because I always forget that one. It's u over the absolute value of u times the derivative of u. Okay, let's remember that absolute value derivative. I know we only did one example.
So-
we never did any homework with it.
You would have us draw it like that.
Yeah, you would just draw two horizontal lines, poles. And I just want to justify it. I wanted to go back and do the algebra to show you why. Like the point of differentiability doesn't work, because you end up getting point of non-differentiability means that the derivative is going to be undefined there. And that's what we're seeing. We're seeing it's undefined at 0. The derivative doesn't work there. It's not going to give us a slope. So if you wanted to find the slope of the tangent line at 0, you're going to say, there isn't one. I don't know what it is. And you can prove it with the alternate form of a derivative too. Okay? Kind of getting it?
The derivative just doesn't exist at that point.
Just at 0. Just at the point of non-differentiability. This is going to get all that non-differentiability stuff we did that made you aware of, you're going to learn now. Because you're going to have to be forced to learn it. Because it shows up all the time, especially in the next weeks. This is your bell curve, so let's see what you think it looks like. Bell curve from statistics. All you get to do tonight is no writing out problems and related rates or anything like that, unless you're going to practice related rates. You're just going to draw pictures today. All I'm going to do. And tomorrow we're going to start physics. Okay, Dave.
Physics?
Mm-hmm. 5 seconds. 5, 4, 3. Alright, here we go. What kind of slopes we got?
Small positive.
They're positive, but they're small positive, right? This is not very steep here. What kind of slopes? You're going to start your derivative above the x-axis, right? But you're going to start it above the x-axis where? When you start your derivative over here, this is all positive. Your derivative is going to be above the axis, but where are you going to start your derivative? Really high or really low or where?
Low.
You're going to start really low, close to 0. And then it's going to get steeper, but then it's going to go back. It's going to get really steep, and then it's going to start approaching a slope of what again?
0.
So where should your derivative cross the x-axis? Because you get a slope of 0, you better your derivative better cross here. Then we go negative slopes. Here's what it's going to look like. It looks really cool. Look how it started out, really close to 0, because those slopes are pretty flat. But they are positive, they're above. Then it gets really steep, and then it says, okay, I'm not going to get steeper anymore, now I'm going to approach the slope of 0. Bam. Anybody get that one?
Sort of.
Kinda?
Drew mine a lot.
You got to get pretty close to the shape. You can't be off in La La Land
I
saying.
drew it a lot bigger.
I didn't write
Okay.
it.
All right. Try the next one. Yes, we're going to pop see this.
Yeah, but you see the announcement though? It's just faculty luncheon.
Oh. I know. Well,
Where's Papacitas?
kind of disappointed. What's the staff lunch?
Subs.
Oh, we gotta eat that. We got a pop see this staff lunch.
It's kind of disrespectful.
Nah.
It's your mouth.
Try it. You're all this.
Your call. You're buying, so it's your call.
Let me think about it.
Because if
We got one more class to think about.
Buy the subs, they're cheaper.
subs are free, they're in
Exactly.
lunch.
They're cheaper.
But that wouldn't be counted as buying me lunch.
No,
Oh.
no, we got one.
Where's Papacitas?
Let me think. Next
You
one.
decide.
Okay.
What?
All right. Have you tried this one?
The gas station.
Okay.
I actually like the way I
The one
finally
off,
do run on home.
Yeah. You're like, yay! I'm gonna finally do something.
Like, Green Bank Community Bank.
Oh, good. I was Oh, yay.
I'm gonna have to bring you in for a bag of. Oh, bag of anymore.
Just take Main Street.
Slope. What slope is this, guys?
0.
What slope is this?
No
Oh,
idea.
And then it's steep positive. So here's what it's gonna look like. Watch.
yeah, I know. I didn't see that one.
Okay. That's neat.
Oh yeah.
It looks like the.
It looks like it.
Kind of like your heart.
Oh yeah. It's called a choo-choo.
Yeah, well, that's what it sounds like. That's just like.
All right, here we go. Next one. This one you should be able to do, no problem. You build some confidence. kind of funny. Ah, you'll get it. You'll get it. Now, think about it. Check, listen, this is what, let me give you some strategies. Number one, see if you see any horizontal tangents. Do you see any horizontal tangents? No. So you can't have any place where it crosses the x-axis. Do you see any points of non-differentiability? Yeah, I see a corner. So you know that there's going to be something unusual happening there. So pay attention at 0 because something weird's going to happen. Now, since there's no place where it's going to hit 0, and we know we got to pay attention at 0 because of a possible hole. Now, guys, if you have a point of non-differentiability, it will reveal itself in one of 3 ways. If it's a point of non-differentiability, it shows up discontinuous in the derivative, which means it'll either be a hole, a jump, or a VA. That's your only 3 options. If you have a point of non-differentiability, then it will show up in your derivative undefined. And there's only 3 ways to be undefined: hole, jump, or VA. Hole, jump, or VA. That's the only 3 points of discontinuity. That's all we learn. Okay? Non-differentiability adds stuff to it because you have discontinuity plus corners, cusp, vertical tangencies. Remember, corners, cusp, and vertical tangencies weren't discontinuous. Okay? That's why differentiability, that's why continuity does not necessarily imply differentiability, but differentiability implies continuity. All right, so I know I've got a positive slope here. What do you think this slope is? 3 or 4 or something like that. So you could have, what would you draw? If this is a slope of 3 and it's always 3, what are you going to draw? Horizontal line at 3. And then this is going to be a slope of what? Negative 3, so this is what it should look like. Come on. You can do it. You did that one okay. Okay? Next one. Try that one. This one will be very, very good for most of you. Okay? This one you should be able to do. Look for this horizontal tangents first. The horizontal tangents first.
And those are just when like that line gets 0.
Huh?
That's when that line hits.
So wherever you have a horizontal tangent, like here, that's going to be a slope of 0, so you know your derivative is going to cross the
0.
x-axis.
Yeah. At that point, okay.
It's Josh Groban. Wow.
Okay, here we go. See how you did. So what I would have done first is I would have said, okay, ooh, I got a horizontal tangent there, I got a horizontal tangent there. That helps me. It gives me some reference points. Gives me some points to head towards. So I know I'm going to cross the x-axis at those 2 places. So just match up your horizontal tangents, and that's where your derivative has to cross the x-axis. So I'm going to go ahead and sketch it. Here it goes. Start out with negative slope, so my derivative is going to start below the x-axis. And the reason it started close to 0 is because it's probably going to go back and do what again? We can't see this, but it's probably a sine or cosine graph. Hits 0, goes up, reaches a steep slope, hits 0, goes back down. There you go. How many got that, or basically got the general shape? Okay?
You got the ends.
The ends will be a little off, and unless I say you don't know for sure if this is a sine or cosine graph. The only reason the applet knows is because it's actually calculating these slopes at these points out. So that's how it knows what these actual y values are. You're just guessing a little bit. So as long as you had it, listen, as long as you had below, above, below, I'm good. You got it pretty close to where it crosses the x-axis. Okay, next one. Ooh. Ooh. I like these weird ones. And we're going to do a couple more, and then I'm going to give you your assignment. I'm going to let you practice for 5 minutes here, and we'll do 2 more. Now think about what you're actually doing here. You're figuring out where the derivative is positive. You're figuring out where the derivative is negative. Where the slopes are going up, where you have positive slopes is where the derivative is positive, which manifests itself as above the x-axis. when the derivative is negative, when the slopes are negative, your derivative is negative, which means it's going to show up or manifest itself below the x-axis. That's really important. That's probably the most important thing you learn. Where you're looking for where positive slopes occur, you're really looking for where the derivative is positive or above the x-axis. Negative slopes tells you whether the derivative is negative or below the x-axis. Here we go. See how you did it. You ready? Really steep. Like so steep, it's so big at the top of your paper. About like that? How many of you did relatively close to something? Good. Okay? Let's do one more and then I'll give you your assignment. Hey. I always like this one. It's like a crevice.
Cusp.
It's cuspy.
Cusp.
We'll call it, I don't know if this is actually a cusp or if that's a vertical asymptote.
Oh,
I don't know how you want to interpret this.
that'd be,
It really kind of depends on how you interpret it. All I know is that there is a point of non-differentiability here, which means the derivative is going to be undefined.
at that point.
Now, how that derivative is going to be undefined, think about it. Think about the slopes, what they're doing, and think about how that's going to show up in the derivative. 'Cause I'm look at this. I'm what kind of slopes here? And then I'm going steep what? And then I come back on this side and I'm what? Steep positive. So think about how that derivative is going to be undefined. Is it going to be a hole? Is it going to be a jump? Or is it going to be a VA? Now these slopes at the end start out close to what? Zero. Interesting. Here we go. Ready? Start out close to zero. Steep negative. It's the boomerang.
Whoa.
Cool.
Booming wave.
Now, assuming this was, I don't know if it was exactly the volcano, but it's kind of like a volcano, right? Like an upside down volcano kind of deal. It's interesting to me that the volcano went to a boomerang. You're going to see that pattern. And I don't know if you've ever done this, but if you start running through the pattern of 1 over x, its derivative is negative 1 over x squared. Then that derivative is positive 1 over x cubed. Wait, does it go 2? I think it goes 2. Wait, that'd be x to the negative 1, right? That'd be negative x to the negative 2, so that'd be 2, right? Watch this pattern here. And then this will be, that's double prime, this is triple prime. And that would be negative 6 over x to the 4th, agreed? The next one, y quadruple prime, would be what? 24 over x to the 5th. And the next one would be y quintuple prime, which would be what? Negative 120 over x to the what? 6th. And if you kept doing your derivatives, your higher order derivatives, what you'll notice you got boomerang, volcano, boomerang, volcano, boomerang, volcano. Because anytime it's an odd exponent on bottom, it's boomerangs. Anytime it's an even exponent on bottom, it's volcanoes. And then the only thing that changes is the signs also alternate. This might be a good question on the test for an extra credit. Figure out the pattern forming and figure out what the 99th one would look like. I think I might ask that. It's a good question for an extra credit.
So you would have to figure out to where
It's going to be
it
like,
would be positive and odd.
yeah, you can figure out where it's alternating and you can figure out there's a pattern at the top. It's not just, it's growing by factors, but it's actually, you notice it's, you'll see it's like a factorial. Okay, any questions? Okay, go to Moodle, I'll show you where your homework is.